Okay, we'll go ahead and get started. Thanks everybody for coming out to talk about tooling after lunch. I know after lunch it's always a little sluggish, so I appreciate Reardon taking the brunt of all that like sleepy energy and waking everybody up. So I want to talk a little bit about dev tooling in a post-covenant world. So we all wake up tomorrow, we have covenants, what now? This is not a talk about OPCAT. I'm gonna use OPCAT to kind of frame the talk and to give sort of a experience report of what it's looked like as we've been trying to build things on top of OPCAT and use that to motivate a discussion about post-covenant tooling. The reason why we're interested in so interested in OPCAT is that OPCAT is incredibly useful. You've heard about this a couple times already. Very simple opcode. You take two elements on the stack, you stick them together on top of the stack. There's a whole song about it. And you can do lots of useful things with that. AJ Towns has like a POW checker faucet on Signet. You can do big num arithmetic by gluing numbers together. And the thing that a lot of people are really excited about CAT is that you can construct or validate hash data structures. So Merkle trees, which some people have been exploring for things like Stark verifiers, but you can also, through some clever tricks, get the pre-image of a sig hash on the stack and then use that to build out a covenant. So this is not a covenants with cat talk, but I wanted to put one slide in it in case you're unfamiliar. If this is interesting to you and you want all the gory details, I gave a talk at Bitcoin++ in Austin this year. It's recorded. It goes through all of the math. It's super detailed. Check that out. Or also, Andrew Polstra did a series of blog posts a couple of years ago that kind of laid the groundwork for that, and it's really good stuff. But the TLDR is that a BIP 341 signature commits to all these fields in the signature. And so if you take all these fields, and some of these are very useful for introspection, things like previous script pub key or outputs or previous amounts, you take all these different fields and you cat all of them together, you do a bunch of hashing, and now you have the S value for a specially constructed Schnorr signature. You call checksig, and if checksig works, then it means that these values must match what's actually in the transaction. So this is a way of getting transaction values onto the stack, and then you can either set them and assert them, or you can assert them by baking them into your script. So that's great. We have CAT. We can do crazy covenant things. We can emulate CTV. We can do things like partially specifying outputs. Let's go build something. How about a vault? I think vaults are a fantastic use case for building covenants because they align really, really well with the kinds of things that Bitcoiners want to use with their Bitcoin. But it's also a really nice kind of hello world for a covenant. It's a useful application that's not like super complicated. You can wrap your head around it because at its core, you can think of a vault as just being a little state machine. So the way to read this is your coins start in this kind of vaulted state. And when you want to withdraw your coins, you commit to where you want to withdraw them to their final target. And that moves your coins into sort of a triggered state. And once they've been in that state for 2 weeks or a month or 6 months or whatever you specify, you can complete the withdrawal by moving those coins to the address that you previously committed to. But the kicker, the thing that makes vaults extra special is that anytime during that waiting period, you can immediately claw the funds back to your vault. So the use case here might be you've got some keys on your phone or your computer or something, and when you want to spend your Bitcoin, there's sort of a waiting period. So if somebody steals your keys, you can get a notification and hit a button and take your money back. This is what you want to do with a vault. There's other applications for things like inheritance, and there's actually a way that you can generalize this state machine to do optimistic challenge response things. But like this is a basic vault. And if we look at this first transaction kind of going from the vault state to the triggered state, this is an easy transaction to imagine. If you think of building a transaction where you have on the input side the funds that are coming from the vault and input to pay fees, and then on the output side, for technical reasons that I'm not going to get into, you kind of send the coins back to that same destination address. And in the second output, you commit to the final destination for those coins. So this is how you set that state that you can carry forward. So if you construct this transaction in your script, the things that you're going to want to validate are things like making sure that the script pub keys match for that first input and first output. You want to validate that this script is running sort of in the right input. You want to validate the amounts, that there's not like a miner who's stealing funds by burning all of your vault funds to fees. And we want to validate that the second output is actually an op return, or is maybe you're sending a dust value to an output or something. Cool, let's go do it. So I actually did write all of this code using Rust Bitcoin earlier in the year. And this is part of it. It's a little bit of an eye test. I'm not going to ask you to read specific lines. The things that I want you to just notice are, one, it's a lot of code. It's a lot of opcodes. When you actually see this script in a transaction, it ends up not being that big because each opcode is 1 byte. But if you notice, there's a lot of comments that have to explain what every single opcode is. And debugging this thing was a nightmare, because what happens is you make this transaction and Bitcoin tells you bad signature, and it turns out that you're missing 1, 2 alt stack, 30 lines down. This isn't all of the code. Here's more of it. And then I had a script fragment that got used in a bunch of transactions. So I was clever and I factored that out into another function, but I had to put this giant comment at the top telling me what the state of the stack had to be before this function runs. So this is now instructions to the human to write your program a specific way, otherwise this script doesn't work. We made a joke about this at 2 weeks ago in TabConf in Atlanta. For the party, we had special Jenga sets made where every single block said opcat on it. So as people were sitting around, they were making giant stacks of opcat, and then the whole thing fell over. Nobody thought it was funny. I thought it was hilarious. But surely there has to be a better way. What we'd actually like to do is, instead of writing the code on the left, which is very verbose and expresses each opcode in a way that's just semantically ambiguous, what we really want to be doing is we want to be expressing what are the kinds of checks that we want our script to do in a way that actually matches our model of the application. Bitcoin script is really meant to be a verification language. You're validating that a set of conditions are true for a transaction, so you'd like to be able to model those conditions with higher level building blocks that you can compose together. So in this case, hopefully you can see the slide. We say trigger the vault. You do a source dest script pub key equality check on the 0th input. You check that the input index is 0. You check that the source dest amounts are equal on the 0th index. And then you commit a value of the withdrawal target in this thing called a caboose. Find me afterwards. It's really great. So we're programmers. A lot of us are programmers in this room. We know how to do this. You take common code. You say, I'm not going to type this over and over again. I'm going to wrap it in a function. Easy, right? Not so fast. It turns out there's a lot of things happening here that make it difficult to just wrap this in a function. If you look, all of the bits that are highlighted in blue have to do with data management on the stack. That is, each section of my script here requires some set of data to be in a particular order on the stack before it executes. That means that if I add another opcode, if I decide that some check needs to come before another one, if I find a bug, I just did it wrong, it means that there's a lot of unrelated code that I have to go and update, and it's not obvious which code you have to update or if you did it right. I pointed out earlier that some of this code isn't even for the computer. It's for the poor meat space person who has to deal with all of this. The code that calls this code also has a lot of complexity. Oh, I think we lost the display. You guys don't have to look at this horrible code anymore. Here we go. It's back. There we go. So this also has a lot of complexity. This entire slide is code that's just working on constructing the witness. So if you haven't done a lot of Bitcoin scripting, the witness is sort of like the inputs for your transaction. Not transaction inputs, but like data inputs. And each of these lines are pushing a value into a buffer that becomes the witness. These have to be the correct values in the right place at the right time, or the script is wrong. This ends up really making things even more complicated than it looks, because if I rearrange parts of my script or add an opcode or add a check, I might actually have related code over here in Rust that I also have to change. This brings up a principle that I've just encountered time and time again, anytime I've been building tooling or abstractions across a lot of different areas, which is it's really, really helpful to try to separate incidental and domain complexity. So I call incidental complexity the problems that you have to solve because of the tools or the technology that you're using, right? Like I'm trying to build a vault. managing data on the stack isn't really a Vault problem, it's a Bitcoin scripting problem. This is undifferentiated heavy lifting that everybody writing complex Bitcoin scripts has to do, regardless of what the application of that script is. That's different from domain complexity, which is the complexity that comes about from the actual problem that you're solving. And the domain complexity is actually where we want people spending their time looking for bugs, looking for issues, and really, really thinking about how to deliver value to their customers or your users or yourself or whoever you're building this thing for. So when you're building complex scripts, whether it's with opcat or without it, there's some amount of incidental complexity that just seems to come up. We've talked about it already. You have data management on the stack, which then ends up making things like data dependencies between the logical components of your script really, really hard to pull apart and to reason about and to compose. Witness construction is a related thing. The data dependencies for these logical components in your script end up requiring data from outside the script, and you have to make sure that you marshal all of that in the right way. The result of this is that it's hard to build logical encapsulations or abstractions of reusable bits of script. What you'd like to be able to do is say, I have a blob of script that validates one thing, I'm going to exhaustively test that thing and then know that I can use it with other bits of script. So, the result of this, like the implications for the poor working engineer who has to do this stuff, is that it ends up being very, very difficult to update or change these things. It becomes very, very difficult to reason about correctness, performance, cost, if it works at all. And you end up, as a result, with a lot of just copy pasta between your scripts, which then when you have to update these things causes just cascading suffering across your code base. So again, what we want to do is we want to figure out if there's a way that we can pull out all this incidental complexity and instead spend all of our time thinking about the actual domain that we're writing our scripts over. So we're working on a project. It's called Katana. Everything that we do has some kind of cat pun in it. And Katana is better tooling for happier cat scripts. It's a Rust library, and we're working towards being able to use it in browser with WASM. We have some customers and some users who really want to be able to do that. And what we're trying to do with Katana is build a set of flexible abstractions that give you a high enough level interface to not have to worry about this incidental complexity, but these abstractions are still low level enough that you can pull back the magic and debug things when things go wrong. What this means concretely is there's not a separate build tool or compiler for these things. It's all just Rust code on top of Rust code. So in your IDE, you can control click all the way down to individual opcodes. So there's a number of pieces that come together that we think makes life easier if you're writing complex scripts. The first building block that really we work on, we call a script gadget. And think of this as like a standard interface for a reusable blob of script. So this is like the simplest possible gadget. I'll show a more complicated one in a minute. But the idea is that you have a little fragment of script, and then you declare what you need the stack to look like before and after your script runs. So you can think of this as like, in a static language, you say like, here's what needs to be the inputs and outputs of my function. This is kind of like a script equivalent. And this is like a really small, simple gadget that you can make. You can also build these things up programmatically. So we have some use cases where you have kind of variadic gadgets where they have different numbers of inputs and outputs. And so we build them out programmatically in Rust, and that's like very straightforward to do. Inside these gadgets, for the inputs and outputs, you see these little representations of data that look like functions, and they are functions. We call these selectors, and the way to think about this is like a variable or a symbolic representation of data that needs to end up on the stack somehow. Now, this data can get there because it comes in through the witness. It can be there because it needs to come from a transaction field, like it's a previous script pub key for one of your inputs, or it might be context. Maybe it's previous transaction history because we're looking back at a parent transaction. Maybe it's spend time application data, like you need to marshal a Merkle tree into your script. It could be a constant, it could be a value that's computed somewhere in the middle of your script. It's just sort of a symbolic way to refer to these things, and you'll see why in a minute. And what you'd like to be able to do is take these gadgets and say, okay, each one declares their input and their output. I'm just going to string them together, just pipe them together one after another, and there's my script. The problem is that you don't get lucky all the time. And sometimes your second script gadget might have different inputs than the outputs of your first one. And so you have to have some glue code or some marshalling code to move things around the stack. So the way that we solve this is, since we have this symbolic representation of what the inputs and outputs of each gadget are, we can build sort of like a virtual memory manager, where before each gadget, we can keep track of where every element is on the stack and automatically insert opcodes to move things around the stack and to rearrange them. A good kind of picture in your head for this is if you imagine that this is the current state of the stack, we draw sort of an index, and we say everything below the index is system memory, and everything above the index is user memory. And the contract, the guarantee that we make with individual gadgets is that when your gadget runs, the user memory will be what you need. It'll be the items that you need in the order that you need them. And between every gadget, we automatically insert the opcodes to marshal things above and below this line, or to move the line itself. So as a developer, this kind of feels like a virtual memory system where you say, hey, I need this variable. And if it's there already, then you use it. And if it's not, the system goes and fetches it for you. But you don't have to worry about that. While we're doing that, like the way that this works is we have to scan through all of the gadgets and keep track of what things are needed for inputs and outputs for all these things. Then we have to insert all these opcodes. While we're doing that, we're also keeping track of what inputs are sort of net new into the script. The reason why this matters is you might have a gadget that has an input that's actually computed from an earlier gadget. So that value kind of comes from inside the script. But then you're going to have some inputs that can only come from outside the script. Think of like a signature, or maybe you're passing in a value for a specific output. So we keep track of what are the net imports of your script, and we build up what's called a query plan. And the idea is that at spend time, all that you have to do as an application author is build up this thing that we call a transaction context. It contains the transaction that you're trying to spend, but then you can also add some additional contextual information like previous inputs or previous transactions. You might have some user-defined values that really matter for your application. There's some other stuff like we provide a nice abstraction for committing to arbitrary data in op returns in a structured way that's efficient to validate. So we have kind of a nice like key value interface that you can use for that. So you build your transaction context, and then using this query plan that our solver has built, you can efficiently build a witness for any of your tap leaves. So putting all these pieces together, the workflow that you end up with, the way that you use this system as a developer, is you author your script, your business logic, by building or using pre-existing gadgets. Like we have a standard library that we ship, and you can also share these things around. You take these gadgets and you plug them together in a way that makes sense for your application, that is semantically meaningful for your application. And then the system will analyze that, create a plan for how to build witnesses, and will insert all of this virtual memory management glue between each bit of script in your script. This all gets baked, it's serialized, it's hashed, it's stable. You can ship it to mobile wallets, you can burn it in, like it all has to be committed in a tap tree. So once you do this step, it doesn't change anymore. And then at spend time, you pass in some transaction context and it spits out a ready to broadcast transaction. So the things that we're trying to solve here with these abstractions, by having things like these composable script fragments, by having sort of automated memory management of stack elements, and by having sort of automated witness building, is we're trying to remove this incidental complexity. We talked about the first two. There's something that I didn't really go over because it would be a very long talk. We also try to remove some incidental complexity around managing a large number of tap leaves, especially if you need to programmatically generate lots and lots of tap leaves. We figure out the efficient ordering and depth in the tap tree for you, and then when you need to spend it, we pull the right one out and build the transaction for you. And we also have been working towards better tooling to make it easier to encapsulate these fragments of script and share them and test them. So off the bat, we've got some hooks for doing like really nice unit testing, where you can take an individual script fragment and run it through a script interpreter, and it'll just tell you if it works. You don't have to build the whole thing out anymore. But we think that this also, in the future, could provide a really nice sort of bounded surface to do things like automated reasoning, right? So we're looking at things like SAT solvers and different constraint solving systems to be able to prove that certain compositions of your fragments do what you think they will. And we also think there's a lot of promise in generative testing. If anybody's ever done like Quick Check or a similar tool, the idea is that you can generate lots and lots and lots of inputs for a given program based on some parameters and then run them through automatically instead of having to write your own tests. And so we think that these pieces put together kind of get you from the mess on the left to actually writing script like the thing on the right, which is a lot easier to look at and reason about. Looking ahead for this project specifically, some things that we're going to be working on in the future are better optimization in those data dependency solving. So right now, there's some cases that you can run into kind of easily where you end up with like more stack manipulation opcodes than is optimal. It doesn't affect the security of your script or the safety of your script, but it takes more bytes. And if we're known for one thing, it's efficient use of Blockspace. So we'd like to, that was a joke. We'd like to shrink that down a little bit. We'd like to work on static analysis of both individual gadgets and composite scripts. Security is the obvious one, but it's very easy when you're writing big scripts to run into policy limits, and it's also very easy to run into consensus limits. A lot of people don't know that you can only have 1,000 items in the stack. That is a very easy limit to run into if you're doing something really complicated in script. So being able to statically analyze your script and say, oh yeah, this is where you're blowing out this limit would be really useful. We'd love to be able to build some higher level abstractions to make this even nicer for common cases. But something that's very important from like a principle perspective is that these are opt-in abstractions that you can still kind of control click your way through. Right now, we're using this tool in Anger internally, building out some interesting applications using opcat. I was hoping to have it open source today, but we're still working on buttoning some stuff up, so it's going to be open source soon. Stay tuned for that. Zooming out a little bit, this is a conference about scaling Bitcoin, upgrading Bitcoin. Why are you all sitting here listening to me talk about like a very specific set of tools for writing cat scripts? Like what is this even about? I think an important part of talking about Covenant specifically, but Bitcoin upgrades generally, is that we need to understand how developers are actually going to use these constructions in practice in order to realize the promise. We've heard a couple times anecdotes about certain upgrades being ready way before the software was. And I think that it's not always obvious how these things are going to be used or if they're usable at all. I think a lot of the conversations that we've had about covenants, and I mean that in like the general sense of either consensus upgrades or just big pre-signed transaction schemes, a lot of those conversations tend to be about things that are technically possible on a whiteboard with zero friction in a vacuum. And I think, something that a lot of people have learned is that the gap between something being theoretically possible and something being productizable and in people's hands in a way that they can actually use it is actually a really big gap. And there's a lot of engineering in that gap that has to go into making these things useful for people to use them as money. So I think something that's important to think about and talk about and work on as we're looking at all these different covenant proposals, and I mean covenant in the broadest sense, is how easy or not is it to actually take these things and build real things with them and to actually realize the value. Some of these proposals might actually be more tooling friendly. They might be less tooling friendly. There might be something that's easier to use kind of on its own if you're hand carving script, but is actually very hard to build tooling around. That's something that we should evaluate, because I think as Bitcoin gets bigger, as we get more developers in, we're going to want higher level abstractions. We're going to want to take all that undifferentiated heavy lifting and kick it in a library somewhere. So we want constructions that are tooling friendly. I think that we should also be thinking about what are the trade-offs around operational overhead, data, cost, all these things with some of these, this is not a talk about grinding like SHA-1 and RIPE-MD hashes, but it's a consideration. Like not all of these things are actually practical for all use cases. I've been mostly talking about a tool that we've been working on. We've been building this tool to handle our use cases, and then I think and I hope that it'll be generally useful for other people, or that there's going to be one little nugget in there that's useful for somebody else and they go build something better with it. But there's lots of other really, really smart people in this space who have been working on other interesting tools for a while to try to pull complex contract authoring up a level of abstraction and make it easier. So one of them, Jeremy mentioned it earlier, is Sapio. It's a really great system for writing state machines out of CTV trees that has like a really nice Rust DSL. There's a tool called script. It's an interesting TypeScript DSL that you write Bitcoin contracts in TypeScript. There's a project called the Bitcoin Wildlife Conservatory. I think Wei King might be in the other room, but he's been doing a lot of really amazing work on trying to build a Stark verifier in script using opcat. And in order to do that, he's had to abstract out a lot of the operations around like Merkle tree validation and lots of math. And recently he added sort of a constraint-based virtual memory system. I haven't dug into all the details, but it looks similar in spirit to what we're trying to accomplish. All these tools are out there. There's more tools that are out there that I probably don't know about. I would encourage everybody who's interested in covenants or who's interested in building big script things, even if they don't use covenants, to check out these tools, play with them, see what you like, see what you don't like, figure out what's ergonomic, give feedback. Everybody loves getting issues on GitHub. Contribute to the ones that you like. I think the only way that we're going to answer these questions is to actually go and try to build things and see what things work and what things don't. Finally, if you like this stuff, and you think that what we're doing is great, or you think what we're doing is terrible, or we're doing it all wrong, or you saw my code and you said, you idiot, why don't you do it this way? That's fantastic because we're hiring. So find me later. I'd love to talk to you. I think we're all out of time, so find me later and I'm happy to answer questions.
As you were describing the problem with all these code fragments, I thought about Miniscript, which you must have thought about too.
Yep.
So I think you can probably take all of Miniscript and like put it into your framework. It just means fewer opcodes, of course, but you would be dealing with territory that's probably well tested. But how are you thinking about this?
Yeah, so one of the first things that we looked at was like, for our set of problems specifically, and this isn't everybody's problems, this is like, we got to go solve our problems. We're trying to build interesting new products and protocols on top of Cat. Part of the reason why we're trying to do that is to explore, like, I have an idea, I think Ethan has an idea, several people have ideas that there's things that we could do with Cat that would be useful to try out and validate, that can prove out demand or utility for Cat directly or for other opcodes. Like I say that a lot, other people say it a lot, we want to actually see it. So we're trying to build that out. So one of the first things that we looked at doing was, can we put some generalized Cat construction like into Miniscript and just use Miniscript itself? And one of the problems that we ran into very quickly is the power and the curse a little bit with Cat is that it's very useful to do lots of different checks depending on like which fields you want to validate and which things. And we ended up, like when we were trying to figure out how to fit that into Miniscript, it ended up making Miniscript very, very complicated to express those things and still have it work with all of the internal data types for Miniscript and for that grammar. So the approach that we're taking now is we're building something that's sort of, I would say it's more user extensible than Miniscript, but we're trying to ship sort of a standard library that covers all the common cases. So we have sort of standard selectors and a bunch of standard gadgets for kind of doing assertions or checks against like all the normal fields in a transaction. That's like what you want to do with Cat. And something that we have some examples around, they're not like in the standard library, but they're in like an examples directory, is we take a lot of common constructions for things that you would do in Miniscript. So we have like a normal checksig operation. We have like an HTLC type thing, like a bunch of things that people do with Miniscript. And we've like modeled those out in our system to see like, how is this to compose and to live with it? I don't think we have any concrete plans right now for like direct interop with Miniscript, but maybe what would be helpful is like if there's common things that people are that we're using our tooling for or other people are, maybe those would be interesting new I don't know, verbs or something for Miniscript.
Yeah, I was more thinking about having test coverage for your way of doing it, because I
Sure.
get that this is a different tooling for a different purpose, but if you want to sanity check your own tooling, you take the exact things in Miniscript and run the exact same fuzzers against it and make sure you didn't screw something up.
That's a great that's a great suggestion.
Dan, we'll do yours really quickly, and then
the conclusion that some of these proposals are easier to make tooling for than others was probably the most interesting thing to me. What's your relative ranking of proposals by ease of making tooling for them?
That's a great question. Like, I should have anticipated that question and come up with like some partial ordering of proposals. I don't have one. I would say something that I've noticed is that the shape of the tooling that you make for like CAT versus CTV ends up being very different tooling in my experience. So Jeremy mentioned earlier that with CTV, what you're really doing is you're building a tree of what are effectively pre-signed transactions, and then CTV takes the interactivity out of that, and you kind of walk backwards up the tree, and then you do a bunch of like hash commitments. So a lot of the CTV tooling is kind of about like, how do we model all of these future transactions and like the fan out in a really like ergonomic way? Whereas the tooling that we've found to be most useful for CAT is abstracting out how do you do like validation or composition of individual things inside of one transaction. So if you saw Jeremy's talk earlier, he kind of talked about programming transactions versus programming script. We found that for CAT, it's easier to build tooling that's programming script. And for CTV, it's easier to build tooling that's programming transactions. I don't have like a strong judgment about which one's better. It's just an observation.
thank you, Rijndael.
Thanks.